Very good. So Christian has a very good question. Where were they before? There are 61 individuals here. There are 61 individuals here. So what we could do is we could Uber analyze each one and say what were they before, their score before, and their score afterwards, and form the difference. The problem with that is we can't scale that at all. In order to scale it, we need a margin of error, which needs a standard deviation. And with a sample size of 1, there is no standard deviation. So the best you can do is this person dropped 36 points. This person raised 2 points. This person dropped 0. This person dropped 2. This person raised 5. Christian?
Well, and just a question that doesn't really relate to
Yeah, go ahead.
Wouldn't it show, or wouldn't it be more statistically valuable if you could show the average change?
Hold that thought.
Okay.
Hold that thought. If you have the data for it, yes. You're exactly 48 hours ahead of us, my friend. I'm going to bring stopwatches next time. I just found a pretty fun little swimming video where we're going to test thumb versus finger speeds on the old school way of checking swim times with stopwatches. It's a research question my old department chair actually posed for me years ago, and I love testing it every term. Yes. The answer is yes. The problem is we don't have that here. All we know is they averaged 100 before, and these are their follow-up scores.
Okay.
So we've got to be as least, we have to have, what's the word I'm looking for? Sig figs, if you will, statistical sig figs. Since we don't have that kind of precision from the inputs, we can't have that kind of precision on the outputs.
Okay.
Love what you're saying, though. Yeah, and we will deal with that later on. There is a slightly fictitious problem with this. And the fictitious problem is the fact that we've said the null hypothesis is equal to 100. I'd like to, instead of saying that, say that here's person A's IQ score before, here's person A's IQ score after. Here's person B's IQ score before, person B's IQ score after, before, after, before, after. And we'll deal with that next time. We just don't have that here. Love it. Awesome. Totally awesome. Totally awesome. Fair enough? Did you guys make me a confidence interval? Was it 1 prop Z in? 1 prop Z in, right? Don't agree with everything I say. 1 prop Z in?
Yep.
Right? What do I put in?
16.
If I'm trying to calculate a confidence interval for the average score, don't I want to use all those data points I just put in?
Sure.
Say it again, Elena. I'm using the wrong interval here. This checks for percentages, proportions. I need the one that checks for averages, which is the T interval. Remember that guy? He was the continuous version of the discrete one here. Yes, we need a T interval. We need a T interval, which is down here number 8, on mine anyway. This looks better. Do we have data?
Yes.
Yes, we just spent that great deal of time putting it in. Go on, just putting this over here. Yes. List 1 is list. What's my frequency? 1. Absolutely. 1. Confidence level of 95? Yes. Yes. Let's calculate it. Takes a couple seconds.
Wait, I have a question.
Yes.
Frequency 1, where do we get the 1?
The number 1.
No, I know,
It's the keypad
Just
one.
hit alpha
Just hit
and
1.
change it to 1.
but what is the number 1? I don't understand.
It only happens
Count all the data points
it
one
only
time.
happens
Oh.
Right, you put one, like this person, this person, this person.
All right.
There's not a distribution. We'll deal with the distribution soon enough, Christina.
Oh, yeah, I just didn't know what
Yeah.
number 1
Oh, for sure.
Okay.
What do you say, friends? Is the IQ, average IQ, Christian? I gotta go with average now because of lack of precision. I love your point, by the way. Can we say the average IQ? The average IQ of acute head trauma sufferers is lower than 100.
Yes.
Yes, because at the highest it's what? About 97, right? Excuse me, puberty. It's a bitch. At the highest it's 97. So it's at least 3 points lower, isn't it? Now the tricky problem is, I'll go back to Susie's again, we're just trying to show that it's different. This actually shows that it appears to be lower. It's all the way down from that. Does that make sense? So we can retest this, and we'll do that later on. I still want it. We haven't done this test yet. Could there potentially be an issue with our data? Think back to T intervals. There are a couple things you should check for before you just run a T interval. And this is in reality, not in this class. In this class, I will give you good data to play with on your exams, because I'm not going to test you on
I'm
that.
like, what if I
But what kind of data should you have in order to use this T interval? It should be roughly bell-shaped, and what shouldn't it have in it? outlier. Why do we care about, forget the bell shapes for a second. The outliers are, I'm way more concerned about outliers, although I do care about the bell shapes, of course. Why are the outliers potentially problematic? The average gets pulled towards them. So if you've got a bunch of low outlier data points, isn't that going to artificially yard the average down? And maybe we shouldn't even trust this. So what should we do, friends?
But you have to take out the outliers on both sides.
Maybe. There might not be outliers on both sides. That's the whole thing. Let's go see if there are any outliers in our data. Two graphs. Two graphs, friends. Just like in 243. Plot one. Let's do a modified box plot on the data. So you're going to set it up exactly like you did for the t interval. I'm graphing L1 with a frequency of 1. I'm graphing a modified box plot. That will give me any outliers and where they are. That'll give me any outliers. Fair enough? Fair enough. That's plot 1. What do you think plot 2 is going to be? We did this all the time at the end of 243. A box plot with a histogram to see if we've got roughly that bell shape that these guys were talking about. It's hard to tell when you have raw data like this if it's bell shaped or not. So I'm going to turn plot 2 on, make it a histogram, and that's set up just fine. Yep. So plot 2 is a histogram, plot 1 is a box and whisker with modified with outliers identified if there are any. Let's take a look. Zoom 9. Look at that. All right, I'm going to do some finagling on the window. I'm going to do a little bit of finagling to get the box plot off the histogram. That's okay with you guys? So I'm going to change, I'm also going to change some of the scaling. The X-Min 73, I'm going to make it 70, what's my highest data point? 124, I think it was. What if I go to 130 and I scale it by tens? That might do it. I'm just changing the X's right now. That might get the box plot off. Nope, not quite. Raise the Y max to 40. That ought to do it. There we go. There we go. Do we have relatively bell-shaped data?
Yes.
I think it's pretty sweet. I think it looks pretty sweet. If you want to, you can make the histogram more refined by knocking X scale to 5. And there it is there. But I don't get anything there that I didn't get in the previous graph. They both look pretty good. All right? Do we have outliers?
Yes.
We do. We do have outliers. Where are they? There are these two out here. So the 124, let's go see what they are. If I trace, it's the 117 and the 124. So let me ask a question. Are they artificially pulling the average down?
No.
From our conclusion?
No.
If anything, they're artificially pulling it up, aren't they? So if anything, the claim we just made that said that IQ is at least 3 points down, it might actually be even more than that if we pulled those out. Your guys' call. Should we pull those out or leave them in? Your guys' call. Leave them in. Because they're not changing the result that we have saying that it's too low. So Bob, with your permission, because these were your hypotheses, can I change this test from a 2-tail to a 1-tail? Because it looks like this is actually happening, doesn't it? Doesn't it look like this? Based on that interval, it looks like anyway. So I think we should test it 1-tail to see that acute head trauma is actually lowering IQ. At least based on this. I mean, if you trace the both curves, look, your median's at 95, right? Your Q1's at 99.5. That means 75% of your data is below 100. Now we kind of knew this already. Damn puberty. Based on Ian's test, right? 75% of the data is below 100. But we knew that because you counted for 16 out of 61 were above. So we kind of knew that already. So it looks not just like they're different, but also it's lower. Is that fair? Please realize on an exam, I would say, test the claim that acute head trauma is lower. I would give you the claim. I like this in class, though. It's more fun to kind of explore ourselves and kind of see what comes up. Fair? So let's test it. We have the variable defined. We have the hypotheses set up. We now need steps 2, 3, and 4. Here's 1. Here's 2. That's going to be a test statistic. We need a p-value. And we need a beautiful conclusion. It either appears or does not appear That what?
Head trauma lowers,
Absolutely. That head trauma lowers IQ. There's the whole thing we have to finish. So in other words, it's identical to what you'll be doing on Thursday and for your out of class next week, except for which test we have to run. Because you can't, remember how we just couldn't run a 1 prop z int? You also can't run a 1 prop z test right now. Because if you try to run a 1 prop z test, you're going to have the exact same problem. You've got x and n, which we don't want. So what do you think we're going to have to run? See if you can figure out the one we got to run in here. What? There was a vote. I heard a vote for a 1 something. It actually doesn't have the number 1 in it at all, believe it or not.
2 props.
Well, no, because we only have one. We only have one variable we're measuring. Thank you, Bob. Only one variable. Patience, my friend, on either Thursday or Tuesday of next week. This will be branching out into 2 and 3 and more variables. I promise you that. Ashley, the one that's just called a t-test. One of the most important tests in statistics is your t-test. I want to go into more detail about it today for sure. It's the one that's called just a t-test. It's near the top on mine. See, mine's at number 2. It's this guy right here. It's this guy right here, just a t-test. It doesn't say 1 prop t-test or 1 average t-test or 1 sample. It just says t-test. This is just TIEs. This is just the way you have to know that. So when you go down to the t-test, go ahead and grab it. I want to talk more about him briefly. He's related to the t-distribution that we talked about with the t-interval. Remember who gave us the t-interval? Remember where it came from? Think back. The Guinness Brewery. Remember Gossett? He needed a distribution to talk about relatively small sample sizes with some level of confidence, and he created the t-distribution. I shouldn't say created, he discovered the t-distribution. That's why it's called a t-test. Now take a look at this. This looks exactly like we need. We have an input, data or statistics. We have data. That's right, we have data. What's the null average in this case? 100. That's what you need. Very nice, very nice. Where's your list and where's your frequencies? L1 and 1 are fine. That's where our data is. And then we have our hypotheses down here, and we're going to be checking less than, aren't we? Because that's our claim right now, is that it lowers IQ. It lowers IQ. Please, Susie, please answer that question.
I always get the wrong one. So when we're picking which one to do, we go off of what we have in our H1.
Always H1. And that's why it's a little hard to catch this. Your TI calls whatever's in 1, this one down here, whatever's in the null, it has a little subscript of 0 in it. So yeah, you pick that one, yeah, and that's going to stay consistent for the next 4 weeks.
Okay.
Fair?
Okay, I'm sorry.
Good? You ready?
Yeah.
Let's draw it. Let's draw it. Yes, please don't.
I'm like, what do we
Look how slowly it grabs.
Yeah.
Why does it grab so slowly? Do you remember why? No, because it's dumb. Do you remember the curve? You can say no, of course.
Because of the head trauma?
Because it's been dropped a number of times. The t-distribution curve itself is burly. The z-distribution curve is actually very straightforward. It's got 1 occurrence of the variable. The t-distribution curve has lots and lots and lots of iterations and gamma functions, and it's a lot more burly than the z curve is. So it takes the TI, even with its computer backing it up, a little bit of time to kind of deal with it. All right? What's our p-value?
0.
Essentially 0. What's our test statistic? Look at that over there. It's negative 4.5, which is negative 4.5 standard deviation below what it should be. What's the variable on that bad boy? Can you see? What's the variable on that bad boy? On the test statistic. What's the variable? The negative 4.5. What does it equal to? Which variable? T. Why T? Because you ran a t-test. So that bell curve right there operates like a z-curve. It operates like a z-curve, but it's the t-curve, which is also bell-shaped. But we need the t-curve because we're dealing with averages, not proportions. We need a different setup. The variable that we need cannot be plotted on a z-curve. It cannot be plotted on a z-curve. A z-curve you have to know your standard deviation for. You don't know what the standard deviation of these IQ patients is. You know the standard deviation of the sample of their IQ scores, but you do not know the standard deviation of the population of their IQ scores. You see what I'm getting at there, friends? So that's why it's T. But as far as that goes, what does the negative 4.5 still mean? it's below average, and it's 4.5 standard deviations below average. It still has the same meaning, it's just a different distribution. It's just a different distribution is all. So what's the conclusion? Does acute head trauma lower IQ? It appears it does, doesn't it? Sure appears that it does. It appears that this is 100 right here. That's where average should have been. We're 4.5 standard deviations down. 1, 2, 3, 4.5. This is where our data lie. Right here. We appear to have a curve over here, which is a lower curve. That's what it appears that we're looking at. Could we be wrong?
Yes.
Of course. How? Which type of error would this be? This would be a false positive, aka a type 1 with what probability? 5%, because we're basing our call at that, comparing it to 5%. Very good. Type 1, 5% potential error. Ashley?
I just have an interesting...
Yes?
Because I actually, in high school I did sports, so they now make you take a concussion test.
Really?
Yeah. So you do all these cognitive things on the test.
Really?
And I did, a couple years after high school, have a traumatic brain injury.
Oh my God.
Yeah, so, but they made me, again, once I recovered a little, they made me take it again to compare the
Indeed.
results.
Christian?
I actually did better than I was in high school. Cognitively better.
Right.
More okay than I was in
No,
high
I love this, Ashley. I love hearing, not to get traumatic brain injury,
Yeah,
of course,
no, it's fine.
but I love hearing the fact that you actually scored higher than you did before. But the question is, on average, what happens to those athletes that have trauma? But right, because that's why you don't want to look at just one. I mean, it's like the story I heard years ago. The head of Philip Morris going, smoking doesn't kill you. Look at me, I've been smoking for 30 years. Yes, you're a data set of one.
Yeah.
You're a data set of one. How about on average? That's the whole point, right? So it doesn't surprise me at all. I wouldn't be surprised if some of these folks went up. I mean, 124. Maybe that was you, Ashley. That was you popping up, right? Who knows? Who knows?
I probably didn't care in high school. It's like, okay.
Or that, but you would hope though that a research study would control for that by the proper kind of filtering process at the beginning. You would hope, and this goes back to Michael's question about the research methods of setting up the experiment. We're defining acute. How is it measured? These cognitive tests, are they reliable? Great questions, and I love this. I love hearing that you went up though, because that's to be expected. That kind of noise within a sample is perfectly acceptably reasonable. Thank you, my friend. Thank you. Fair, believable-ish. So the only thing that you have to remember, and it's not important to memorize formulas, because it's the same formula that you use for the t-distribution, is you're running a t-test on the averages versus a z-test on the proportions. That's it. That's it. Just like before. Just like before. Z's for proportions, T's for averages. It's the same exact difference. Same exact difference.
So we're not doing this on the test on.
No.
No, that's why we have like a mild freak out. I'm like, oh my God, why is he teaching us this? I don't understand.
Because we had time.
No, I know, but I'm like...
And because the conclusions are still the same, are they not?
Yeah.
And the error identification is still the same, is it not? The only difference is the slight difference in hypotheses.
No, I know,
That's
but
the
I was
only...
just like, how do you remember
Oh,
all
relax,
this?
my friend. Breathe deeply, breathe deeply. Cool?
Yeah.
Let's look at one more and then call it a day. A little more, call it a day. And then next time we'll do the measurement ones, the one that actually involves stopwatches and things like that. Okay? Because these are great. But unfortunately, they do require a bit of fiction, which we'll come back to on Thursday after your exam. Look at the speed limit ones down here. Neighbor data and police data. And see if you can answer the question, which, if any, of those data sets indicate that cars are speeding? Which, if any, of those data sets indicate that cars are speeding? Which, if any? Which, if any? Oh, and I'll pause this while you guys...